Hello, everyone. Professor Gillies and myself are here to talk about the climate effects on the debris flow risk. So we're here to provide you with more or less a 30,000 feet perspective on flood risk.
As director of the Climate Centre, I'm responsible for climate services for the state of Utah. Very much involved with research on the Intermountain West. We were taking our research and put it into an operational capacity in terms of prediction of certain climate phenomena.
My name is Wang, I go by Simon. I work in Plant, Soils and Climate Department, in particularly the climate program. I try to understand why there are climate extreme events. By training, I'm a meteorologist as well.
Flood risk doesn't form just overnight. It takes time for the climatic and environmental conditions to converge. One of the concepts is that the flood risk involves the build-up process. I'm showing here an example for the 2011 Missouri River flooding. And you can see that within the Missouri River basin, these time series are the satellite inferred groundwater. And these come from 2003 all the way to the flood event in 2011. And you can see that a couple of years before the event, you see this big build-up process here, leading to the eventual collapse of it. That coincides with spring storms. So you can see that it's a typical perfect storm scenarios, right? Like you have the environment that is prone to discharge, and when you have a weather event that coincide with it, and then it's a recipe for a great flood. The second concept is climate cycles. Here in the Intermountain West, we have observed from multiple lines of evidence that our climate and hydroclimate has undergone quite repetitive cycles over time. Zach mentioned about the debris flow. A lot of the debris flow came from fire scars. And the post-fire debris flow, they came from a cycle that involved drought and then fire and then a wet event. And Utah is not foreign to fires, as we can see here from the recent events. Here is a fire burn scars leading to flood risk or debris flow. I think it's quite intuitive, right? But if you reverse it and then lengthen the time a bit longer, you're going to see that climate plays an important part in these fire cycles. After each burn, the forest regrow, right? And then the vegetation regrows too. And during the regrowing process, it's deeply affected by climate, favorable climate conditions, coupled with a mild summer. All these factors eventually determine how fast and how broad the vegetation cover grows. When it grows to be prone to fire danger, and fire weather becomes an important factor. So you can see that in this forest regrowth and burn cycle, climate affects how sensitive it is to fire.
Utah is interesting that it actually has these two regimes, the northern regime and the southern regimes, which are actually driven by different climate drivers. We found a connection between the sea surface temperatures in the Western Pacific and the rainfall seasonality in northern Utah. We've also been able to use that connection to forecast the elevation of the Great Salt Lake.
In our regions, we have seen a few big events of floodings happening in the past. And you can also see that from the satellite-derived groundwater data, that shows a slow transition. That the flooding events usually coincide with the water level buildup. We don't really have the earlier data for 1923, but we could use the climate reconstructions that was built from the tree rings. Here's the explanation from Dr. Justin DeRose of Utah State University, who is a tree ring scientist.
We've sampled a number of sites in the West for tree ring data. And what we do with dendro data is we sample trees to tell us a story about, in particular, past climates. The greater Wasatch Front region has exhibited strong shifts between wet periods and very dry periods. We're able to extend those reconstructions back 1,000, possibly 2,000 years. By telling us what happened in the past, they give us an idea of what might happen in the future.
Let me demonstrate how you can access the tree ring reconstructed stream flow through the Utah Climate Center webpage. You can go to Draw Informatics System. You can go through different variables, from snowpack to soil moisture, and then in the middle of it, it's the stream flow. Then you can select different major rivers. So you click that. This is the Bear River flow, okay, reconstructed for more than 1,000 years. So the most recent ones are here in the red. So these are the stream gauges. So you can see the cyclical behavior that oscillate between about 10 to 15 years. And if you reset it, then you can see how the stream flow varies in the past. We have seen some high flows in the past. You can also see some of the recent events. For example, 2017 is one of the high flow, right? And then 2005, another one, although it's really not a peak flows. But we have to consider it is the build-up process that coincides with weather events, which, under the warming conditions may not become so random at all. So 1923. Okay, so looks like it's one of the high flows as well. The stream gauge doesn't go back that far, but the tree ring reconstructions can tell us the variability of it.
I'm going to just let the music play out, and I'll just fade out in just a minute. So, for example, this is the violin, and that was a piece from the Fry Street Quartet. So the voices of these instruments, which have both pitch, tone, all of these things, is analogous actually to the climate system. The climate system has a voice, and those voices are characterized just like this, and we have some fancy names for them. So for example, we start at the top there, where things move very, very quickly, and that's called the Madden-Julian voice. Then we have El Nino, which you've probably all heard of, the El Nino Southern Oscillation. And then we have one called the North Atlantic. We have the Quasi-Decadal, and the Pacific Decadal, and the Arctic, and there are many more. So these voices are actually pulsing throughout the climate system, and they affect our climate in very interesting ways. So here's the Madden-Julian oscillation, or voice, okay? And you can see it simply consists of warm, cold, pulsing across the Western Pacific. What is happening there affects what happens in our weather. The energy is transmitted northward to North America. And so this pulse of energy that is continuously going across and resetting every 48 days is sending energy northward and affecting our weather systems. And this one is particularly relevant because it's responsible for our inversions.
We can apply really the soil, water, and also the total water storage concept, because it's like a reservoir underground. In northern Utah, this floodplain and groundwater are tightly linked to the Great Salt Lake and also the base flow of it. So in a normal drainage basin or an open outlet lake or river, this is what you would see of the flow accumulations, right? So that, first of all, the surface water will come in, and then you have this seasonal cycle of snow melt and then summer drying. That's the blue part. But then slowly the base flow will catch up and then continue to ingest water into the lake or the river. But for the Great Salt Lake, because this is closed basin, a base flow process, the green one, it's much profound. It creates something that is called a reddening effect, caused by a large water body like ocean. And that creates slow changing variability, naturally. This is the raw data. I know we didn't really do any smoothing. You can see that, the lake leaves the footprint of the low frequency variability. If we can capture the relationship between the base flow and the slow changing climate variability, then we can potentially monitor or even predict how the water storage will be, and then by coupling it with the hydrological model to assess the flood risk. The next explanation will focus on the Wang and cold anomalies in the Central Pacific Ocean.
This is a little tricky. This is the quasi-decadal oscillation. So this is this 12-year oscillation. So what we have here initially is sea surface temperature in the tropics, and the yellow is hot to cold. And I have a little animation here to help you understand this. If I go from there, from a crest to a crest, that distance is about 12 years. So this oscillation, this voice, lasts 12 years, okay? Now what is very interesting about that is that if you go from a crest down halfway, that's about 3 years, okay? So you're transitioning from warm to cold. 3 years from that transition from warm to cold, guess what? The precipitation peaks in Utah. So we have a 3-year phase lag between the sea surface temperature and our maximum precipitation here in Utah, okay? And then, even further, if we look at a peak of the precipitation, again, this is 12 years from peak to peak, follow that halfway down from high precipitation to low precipitation, and guess what? The Great Salt Lake elevation peaks there too. So that's really quite interesting then, because now you've got a connection between the tropics, our precipitation, and the Great Salt Lake elevation, all of which have a lag of 3 years. And when we first discovered this, and that was the first paper that we wrote, we thought, can we use this as a predictive tool? And sure enough, okay, we can. Now, of course, taking this data, the sea surface temperature, and the precipitation, and the linkage between the two, we were able to forecast the Great Salt elevation, this, out to 8 years. But the most important thing about this, so combining the two time series and also knowing the linkage between the Western Pacific and our precipitation regime allowed us to go out 8 years, but more than that, it actually allows us to forecast the turnaround points, which could never be done before.
There's one concept that we like to introduce you is the variability. When people hear climate or climate change, they often think about this long-term indication of the future or projections. And it's really often not the case, especially in our region here in the Intermountain West. We have a very profound variability that comes into almost like a cyclical behaviors. But there is also the climate trend, and the trend can tip the scale into these extreme categories when they overlay with the variability, like we're seeing in the red line here.
How about precipitation? Well, this is interesting. We're actually getting more precipitation. We're wetter, okay? But less of it is falling as snow, but more as rain. Here's snow depth, for example, from 1950. So this is from the paper. And you can see the variability, but you look at the trend line, the snow depth has been decreasing since the 50s. Okay? And the interesting one is the snow to rain ratio, where you actually take the amount of snowfall and you divide it by the amount of rain, okay? Less snow, more rain. But then the winter storms have become less frequent. This year was a classic example of that. We had, 4 major storms, and that was about it. But these systems are becoming less frequent. Here's the data. So here's the precipitation, the frequency, over from 50s up to present. Precipitation is going down, snowfall is going down. So precipitation is going up, but the frequency of storms is going down. Is that a conundrum? What must be happening? Each storm is dumping more precipitation, and it's doing it in a more intense way. So we're getting more intense events, less of them, but they're dumping far more precip, but more as rain.
So next we'll be talking about risk from heavy precipitation events. So we will introduce the concept of PMP. So let me briefly explain what probable maximum precipitation, or PMP, is. To track storms, we try to identify the storm's occurrence, location, and movement, and then we estimate how much water it could possibly rain out from the sky. We do that for each different seasons, and we track it for every day throughout the year, and then year after year to form a climatology. So after we do that, then we have to separate them or categorize them into different weather types, from monsoons, fronts, and then we start to estimate how extreme they could be. And year after year, and we produce a PMP case table for that. And this will become the background of the PMP informations. So PMP can be estimated from stations or from graded observations across the state. The more modern approach is to use this 4-dimensional atmospheric reanalysis. So it sounds simple, but the computation of it takes a lot of time and effort in coding and computer numerical simulations of it. So then we generate maps like this, and then each point indicates the value that we can be applied to estimate the probable maximum precipitation. So we did compute the PMP for the entire state of Utah. And here's a graph that we extract the data for the Bear River outlet. You can see that the PMP for this particular region has an increasing trend starting from the 1980s. Each bin spans for about 5 years. So you can see there's a consistent increasing trend in the past 40 years. So you wouldn't be surprised if climate models are depicting an increased trend. We are processing the data. It's not surprising because as the air warms and it tends to hold more moisture, when the atmosphere forms the conditions that is prompt to thunderstorms, and each developing storms could potentially produce more rainfall. And this relationship is not linear. So, a small increase in the water vapor content in the air can lead to a large increase of rainfall. To recap, large fires lead to potential for debris flows, and that fire cycle also involves climate factors. The hydroclimate in this region undergoes a robust wet-dry cycle, and it outweighs the long-term trend, and this deserves our attention.